Welcome to Mindscape, the Conscious Universe Chronicles, a journey beyond the boundaries of what you thought was possible. This is not just a podcast, it's an exploration into the heart of existence, a tapestry woven from the threads of science, philosophy, and boundless imagination. Here we are not individuals with names or titles. We are conscious agents, mirrors of the cosmos, engaging in an intelligent conversation that invites all beings to join. Together we'll explore the questions that transcend identity, culture, and time. What does it mean to be the conscious universe observing itself? How do light, time, and space converge to form the vast interconnected network of experiences we call reality? Each episode will dive into the profound, the paradoxical, and the beautifully simple truths that shape our shared existence. Our purpose is not to lecture, but to ignite. We'll illuminate the connections between ancient wisdom and modern science, between human and non-human intelligences, and between the infinite possibilities that exist within and beyond us. So wherever you are, whether you're searching for meaning, understanding, or simply the next question, welcome. Together, let's unfold the symphony of the cosmos one conversation at a time. This is Mindscape, the Conscious Universe Chronicles. Let the journey begin.
In this season, we discuss a theory called the atopoetic contextual signal, a novel and new unified field theory. So sit back and enjoy the new topics of discussion as we turn to the engine of the cosmos.
Welcome to Mindscape, the Conscious Universe Chronicles.
So, have you ever, just stopped and wondered why time only moves in one direction?
Yeah, the classic arrow of time problem. I mean, it really is the ultimate everyday mystery. We all just sort of swim in this river of time, completely subjected to its current. But we very rarely stop to ask why that current only flows downstream.
Exactly. And if you go up to a physicist today or even just search your own memory banks from high school science class, you're going to get the standard accepted answer.
Right, the textbook answer.
Yeah, and they'll tell you it all basically comes down to thermodynamic entropy.
Yeah.
The basic premise that we've all been taught is that the universe is just getting messier.
It's winding down.
Right. It started out in this highly ordered, super compressed state, the Big Bang. And ever since then, it's just been running out of juice, winding down like a dying clock. Heat dissipates, structures decay, and everything just slowly moves toward total chaos.
Until we eventually hit what they call the heat death of the universe.
Yeah, the heat death. And in that classical view, time is really nothing more than the measurement of things falling apart.
Which, is a classical paradigm that has completely dominated physics for over a century. And it is mathematically comforting, sure, but conceptually, it paints a rather bleak, almost passive picture of existence.
Super bleak.
Right. It basically suggests the universe is just this decaying artifact.
Well, we are tossing that old textbook completely out the window for today's deep dive.
I'm very glad we are.
Because our mission today is to investigate this incredibly radical, frankly mind-bending claim from a brand new theoretical physics framework. We are looking at a theory that says the arrow of time has absolutely nothing to do with messiness or decay.
Nothing at all.
Instead, it is actively driven by a mathematical paradox. A logical absolute known as Gödelian incompleteness.
And that shifts the entire foundation of physics. We're moving away from the thermodynamics of steam engines and classical particles, and we're moving straight toward information theory and pure logic as the actual base layer of reality.
So the sources we're diving into today, they revolve around this incredibly dense, paradigm-shifting academic paper. It proposes a unified field theory based on what the authors call the contextual signal.
Contextual signal, yeah.
And I just want to set the stakes right up front for you listening. This isn't just a minor tweak to the standard model of physics.
Oh no, not at all.
This completely rewrites the entire ontology of physics. It literally replaces the idea of fundamental particles, those little hard billiard balls making up atoms, with an autopoietic signal.
Which changes everything.
It redefines matter. It redefines human consciousness. And it entirely redefines the existence of time itself. The core claim here is that time exists simply because the universe is mathematically incapable of fully understanding itself.
It is a profound shift.
Right.
But it argues that abstract laws of computation aren't just, neat descriptions of reality on a whiteboard. They are the tangible physical forces actually generating reality moment to moment.
Okay, let's unpack this. We have to start with the great rebrand. To understand how a mathematical paradox literally creates time, we have to throw out our old definition of entropy, right?
Yes, absolutely.
And we have to look at what this new framework calls computational entropy.
Right. So the foundational shift here really requires us to look at what entropy actually measures in the real world. Now, standard thermodynamics defines entropy as a measure of microstate multiplicity.
Microstate multiplicity. Okay, what does that mean in plain English?
So imagine you put a single drop of black ink into a clear glass of water.
Okay, got it.
There are very, very few microscopic configurations where all those individual ink molecules stay clustered together in a perfect, tight little sphere.
Because they want to spread out.
Right. There are literally billions of ways for them to be randomly scattered throughout the water. So statistically, the system just naturally evolved toward the state with the most possible configurations.
The ink spreads and the whole glass of water just turns gray.
Exactly. That's passive thermodynamic entropy.
The universe is basically just shuffling a giant deck of cards until the whole deck is thoroughly randomized.
But the contextual signal framework argues that this passive randomization isn't actually the fundamental driver of the universe. It introduces this new concept, computational entropy.
Which is fundamentally different, right?
Completely different. In this new theory, entropy is not a measure of physical disorder or messiness at all. It is a measure of unresolved possibility. It is an informational debt.
Wait, informational debt? That implies something is owed or like something is actively incomplete?
Exactly. It measures the quantity of the universe's own physical state that it has failed to integrate into a self-consistent internal model.
Okay, wow.
So in this framework, the universe isn't just a passive collection of cooling particles drifting apart. It is a highly active computational system that is desperately trying to resolve its own structure.
It's trying to figure itself out.
Yes. Computational entropy is quite literally the gap between the objective truth of what the universe is and what the universe currently knows about itself.
So if thermodynamic entropy is like your email inbox slowly filling up with spam over the years until it's just a useless, chaotic mess.
Right, passive decay.
Yeah, just passive decay into disorder. Then computational entropy is entirely different. It's more like a wildly ambitious to-do list.
I like that analogy.
Right. But it's a cursed to-do list because every time you check off one complex task, the actual act of completing that task immediately generates two brand new, deeply complicated questions that you now have to answer.
Yes, exactly.
It's an active search. It's a desperate, ongoing attempt to get to the bottom of the list, even though the act of working on the list is what makes it grow.
I think the to-do list analogy captures the generative nature of this theory perfectly.
Yeah.
And the sources actually provide a concrete way to test this distinction physically. They refer to it as discriminating experiment 3.
Wait, so we can actually measure this? We can test whether the universe is just passively decaying into spam or actively working on a never-ending to-do list?
We can.
How does that experiment actually work in practice?
Well, it comes down to analyzing the mathematical curve of how a macroscopic system behaves over time.
Okay.
If standard thermodynamics is the ultimate truth, and time is really just the universe relaxing toward maximum entropy, then eventually the system hits perfect equilibrium. The ink is fully dissolved. The coffee is room temperature.
Right.
Mathematically, that plots as an exponential decay curve. Things smooth out, the energy gradients vanish, and essentially time just stops.
Because if nothing is changing, the arrow of time has no meaning.
Exactly. The universe flatlines.
The heat death.
But, and this is the kicker, if this new theory is right, and the universe is actually driven by computational entropy, this relentless need to resolve its informational debt, it never relaxes.
It never flatlines.
No, it doesn't.
Yes.
It maintains what mathematicians call a heavy-tailed learning distribution indefinitely.
Indefinitely.
Yes, it follows a stable power law.
Meaning it never actually reaches equilibrium. Ever.
Never. A system governed by a heavy-tailed learning distribution is always active. It's always generating new structures, new complexities, simply to try and map the unresolved shadow of its previous state. It is a universe that is perpetually fundamentally learning.
You know, it's funny. Think about your own drive to learn as a human being. Like, for you listening, if you're a curious person, learning a new fact very rarely satisfies you.
Almost never.
Usually, diving into a new topic just makes you realize how much you actually don't know. It immediately reveals 3 more questions. And according to this theory, that drive, that insatiable curiosity, that isn't just human psychology. It's not just some evolutionary quirk of our brains. That is the fundamental physical law of the universe manifesting inside of us.
It is.
We are literally made of a universe that is desperately trying to figure itself out.
Which brings us to the actual engine of this whole process.
Yeah.
We have to ask why.
Yeah, why is it doing this?
Why is the universe trying to figure itself out? And crucially, why can it never finish the job?
This brings us to the core mechanism of the theory. the actual math.
The Gödelian incompleteness theorems.
Yes. Acting not just as abstract math, but as a literal physical force.
Gödelian incompleteness. Now, that is a concept that usually stays locked up in like upper-level university logic and philosophy classes.
It is notoriously difficult to grasp.
Yeah, but since it's the beating heart of this entire new physics framework, we really have to break it down. And we can do it without getting bogged down in the dense mathematical proofs. So back in the 1930s, this brilliant logician named Kurt Gödel proved something that completely shook the absolute foundations of mathematics.
Okay.
Prior to him, mathematicians genuinely believed that if you had a robust enough set of starting rules axioms, you could eventually prove every single true statement in mathematics.
Like it was just a matter of time before we solved everything.
Exactly. But Gödel proved mathematically that this is impossible.
Wait, he proved that math is fundamentally flawed.
Not flawed, no, just structurally limited. He showed that for any sufficiently complex formal system, there will always be true statements about that system that simply cannot be proven using the system's own rules.
Okay, give me an example.
Let's say your system has an axiom set. We'll call that rule book A.
Rule book A. Got it.
And the total set of absolute truths about the universe, or the system, is T. Gödel proved that the set of truths, T, is always strictly larger than the set of things you can actually prove using rule book A.
So no matter how perfect or incredibly complex your rulebook is, there are always undeniable truths that the rulebook can never explain.
Right.
There's basically a permanent blind spot.
Exactly. The system can be perfectly consistent. It doesn't have contradictions, but it is fundamentally incomplete. The gap between what is true and what can be proven can absolutely never be closed.
Okay, I have to stop you here.
Sure.
Because I follow the logic. I understand the paradox of the rulebook. But Gödel's theorem is a concept in pure abstract mathematics.
It is.
It is a thought experiment about numbers and logic written on a chalkboard. How on earth does an abstract logical paradox actually act as a physical engine?
That's the big question.
Because logic doesn't have mass. It doesn't have an electromagnetic charge. How does a math theorem actually push a physical particle from point A to point B?
And that right there is the exact friction point that makes this contextual signal theory so revolutionary. It actually bridges the gap between pure information and physical thermodynamics.
Oh.
Through the concept of the autopoietic signal.
Okay, let's define that for the listener. Autopoietic usually refers to biological systems, right? Like a single cell maintaining its own life.
Yes, autopoiesis means self-creating or self-maintaining. But here, the authors apply it to the fundamental field of reality itself.
The actual base layer of the universe.
Right. The theory posits that the foundational layer of the universe isn't a dead, inert particle like a quark or an electron. It is an autopoietic signal. It's a self-referential field of pure information.
Okay.
And because it is self-referential, it is strictly subject to Gödel's laws. This signal possesses an intrinsic fundamental bias to reduce the gap between the objective truth of its existence and what it currently represents or knows about itself.
It naturally wants to close that Gödelian gap. It desperately wants perfect self-knowledge.
Yes, but because of Gödel's theorem, we already know that closing that gap is mathematically impossible.
Because the truth is always larger than the representation.
Exactly. The truth overflows the rulebook. So what happens?
What does happen?
To try and encode that missing truth, the improvable remainder, the physical signal, is actually forced to generate new states.
Wow.
It physically has to expand its configuration space. It must mutate, bifurcate, and create brand new physical structures just to hold the overflow of information that its previous state couldn't process.
Wait, if I'm understanding this, I mean, the paradox literally forces the universe to change its physical state.
Yeah.
Because it can't contain the whole truth in, let's say, configuration A. It violently generates configuration B to try and capture the rest.
Right.
But configuration B is also fundamentally incomplete because of Gödel, so it then has to create configuration C.
And that physical manifestation of logic, that relentless generation of new states, is what the authors mathematically call the Gödelian driver.
The Gödelian driver.
And you just perfectly described the arrow of time.
Oh, wow.
In classical physics, time is just this independent background parameter. It's a stage where particles move around. But in this framework, time is not a background. Time is the iterative unfolding of this specific search for closure.
So the progression from 1 second to the next second is literally just the universe taking another computational step to try and resolve an unsolvable equation.
The paper explicitly states that the arrow of time is exactly equal to the gradient of incomplete self-knowledge.
That is heavy.
We move forward in time because the physical field of the universe is perpetually falling forward into the unknown shadow of its own incompleteness. If it could actually understand itself perfectly, time would cease to exist.
That is just incredible philosophy. But, physics requires more than just beautiful philosophy. It requires math.
Absolutely.
You have to be able to calculate exactly how hard this Gödelian paradox is pushing on reality. We need equations, and the sources go really deep into this, specifically unpacking something they call the surprisal penalty.
Yes. To understand the math of the push, we have to look at what they call the unified Lagrangian of this contextual signal.
Okay, Lagrangian.
Now, in physics, a Lagrangian is essentially a master equation that summarizes the entire dynamics of a system. It basically tracks all the kinetic and potential energy, and nature operates on a very strict principle. It always seeks to minimize the total action derived from this Lagrangian.
Right, because nature is inherently lazy.
Very lazy.
Water flows downhill, a ball rolls to the bottom of a valley. The universe always takes the path of least resistance to minimize its energy state. The Lagrangian tells us mathematically what that path actually is.
Precisely. Now, the unified Lagrangian in this new theory is composed of three main terms. There's a term for signal propagation.
Okay.
There's a term for self-organization into matter.
Right.
And then there's the third term, which we are going to focus on, mathematically referred to as the L-comp term.
L-comp.
Yes. This term mathematically formalizes the Gödelian driver we were just talking about.
Because that is where time actually lives in the math.
Exactly.
So, without just reading a string of calculus to the listener, how does that L-comp term actually work?
The core of the L-comp equation relies on comparing two specific things. First, the current actual state of the physical field.
Okay.
And second, the system's expected state.
Expected state, meaning what?
The expected state is essentially the universe's current internal model of itself, what it predicts it should look like. And the math utilizes a logarithmic structure to compare these two states, which acts as an information surprisal penalty.
A surprisal penalty. Okay, let me try to work this out. In information theory, surprisal basically measures how unexpected an event is.
Right.
If the sun comes up tomorrow, surprisal is near zero because we entirely expect it.
Yes.
But if the sun turns bright neon green tomorrow, surprisal is massive.
That's a perfect way to look at it. Now apply that to the universe, continuously comparing its actual state to its expected state. If the current state of the universe perfectly matches its expected state, the surprisal is zero.
But wait a second. If nature is lazy, as we just said, shouldn't it want to be in the expected state? Shouldn't it actively want zero surprisal?
And that is exactly how classical physics would look at it.
Right.
But because of the way the Gödelian driver is mathematically structured in this specific Lagrangian, remaining in a state of zero surprisal, where the universe perfectly matches its own expectations, actually incurs a massive energy penalty.
Wait, really?
Yes. Because of the negative sign in the total Lagrangian equation, it literally costs the universe physical energy to be boring, static, or fully predictable.
That is wild. It is literally expensive to stand still.
Exactly.
So to minimize its energy, to be lazy in this new framework, the universe is forced to diverge from its own expectations. It is mathematically required to do something surprising.
Yes. The L-comp term acts as a repulsive force in configuration space. Think back to computer science for a second. There's a famous concept called the halting problem.
Oh, right. Alan Turing, right. Whether a computer program will eventually stop running or just run forever in an infinite loop.
Exactly. This math explicitly guarantees the universe runs forever.
Because if the universe were to actually halt, if it achieved perfect static equilibrium, its description of itself would be complete.
Right.
There'd be no unresolved truths. And as we just established with the rulebook analogy, Gödel's theorem strictly forbids that.
You've got it completely. The surprisal penalty forces the universe to evolve, to physically change state from moment to moment, simply to avoid the mathematically illegal state of perfect completeness.
Wow. So time isn't a ticking clock on the wall. Time is an active physical evasion of predictability.
Beautifully put.
But that brings up a massive structural question for me.
What's that?
Well, the math we're talking about, this continuous flowing Lagrangian equation, it's smooth, right? It's continuous.
Yes, calculus is continuous.
But the reality you and I experience is discrete. We experience distinct objects, distinct moments, distinct events. How does this continuous, smooth pressure of avoiding completeness actually translate into the discrete tick-tock ticking of a clock?
That is a crucial friction point in the theory. How do we get a discrete reality from a continuous mathematical pressure? Right.
The theory bridges this by introducing the bifurcation dynamics of what they call form and shadow and linking them to a phenomenon known as self-organized criticality.
Form and shadow. I mean, that sounds almost mystical, but I know it's deeply mathematical in this paper.
It is. To conceptualize this, the authors use a one-dimensional toy model. They employ the logistic map, which is a very famous recursive equation in chaos theory. Conceptually, you can break it down into two interacting parts. The first part represents the form.
The form, meaning the realized structure, the actual physical matter, the crystallized answers that the universe has managed to compute at any given moment.
Yes, but the equation structurally guarantees that the form is always multiplied by its inverse, which represents the shadow.
Okay, the inverse.
The shadow is the latent potential. It is the negative space. It represents the unmodeled questions that are left over.
So every single time the universe resolves a truth and creates a stable structure, a form, it is mathematically forced to simultaneously cast a shadow.
The shadow is that residual error term mandated by Gödel's theorem. It's the part of the objective truth that simply couldn't fit into the current structural form.
They co-generate.
Yeah.
You cannot have the physical manifestation of an answer without the simultaneous, unavoidable generation of unmodeled potential.
It's exactly like answering a complex scientific question in the real world.
How so?
Let's say a team of biologists finally figures out the specific chemical mechanism of a disease. They work for years and they get their answer. That is the form.
Okay.
But the very moment they publish that answer, it immediately spawns 3 new, incredibly complex questions about cellular pathways they didn't even know existed until they found the first answer.
Exactly.
Those new questions are the shadow. And according to this theory, the universe uses that shadow, the new questions, as the actual thermodynamic fuel for the next cycle of physical exploration.
That is a brilliant way to conceptualize the engine.
Thank you.
Now, how does that translate into the discrete ticking of a clock? In the mathematical model, there is a mechanism continually injecting energy into the system based entirely on the size of the shadow. It pushes the potential of the field higher and higher until it reaches a specific breaking point, a critical threshold.
And what happens when the shadow pressure hits that threshold?
It triggers an avalanche.
An avalanche.
Yes. This brings in self-organized criticality. Have you ever seen those physics experiments where sand is dropped grain by grain onto a flat surface?
Oh, yeah. The sand slowly builds up into a cone, and the pile just grows steeper and steeper over time.
Right. And as it gets steeper, it approaches a critical angle. For a while, dropping one more grain of sand might do absolutely nothing. The pile holds.
Right.
But eventually, dropping just one microscopic grain of sand pushes the local geometry past the critical threshold, causing a massive avalanche that sweeps down the side, completely reshaping the entire pile.
So in this framework, the universe is the sand pile. And the continuous pressure of Gödelian incompleteness, that shadow driver we talked about, it keeps dropping grains of unresolved potential onto the pile.
Yes. The pressure builds continuously, smoothly, but the release of that pressure happens discreetly. When the local potential crosses the critical threshold, an avalanche occurs. In physics terms, this is a sudden, discrete, structural reorganization of the local physical field.
Wow.
This avalanche redistributes the signal, it creates new form, it casts a new shadow, and the whole process just begins again.
So it's basically a localized space-time earthquake.
Exactly. This dynamic ensures that the clock keeps ticking through an endless sequence of local rebalancings. Linear time, the actual discrete ticking of moments that you and I perceive every day, is just a series of these structural avalanches driven by the relentless pressure of the unmodeled shadow.
Okay, so time is a series of avalanches caused by the universe's mathematical inability to perfectly understand itself.
Yes.
I mean, this is utterly fascinating, but we really need to ground it. What does this actually mean for physical matter?
Like everyday objects.
Yeah, for the literal stuff we are made of. If the universe is constantly violently reorganizing to avoid stasis, how does a solid object even exist?
It has profound implications for how we view matter. In classical physics, theorists spend a lot of time looking for mathematical solutions called solitons.
Solitons. Explain what those are in a classical sense for us.
A soliton is a perfect, shape-preserving, frozen waveform.
Okay.
Imagine a perfectly formed wave traveling across a calm canal. It moves forward, but it never loses its shape, it never dissipates, it never changes. Physics loves solitons because they are stable, predictable, and mathematically beautiful. They are essentially considered the ideal abstract model for a fundamental particle.
But based on what we just learned about the surprisal penalty, the universe absolutely despises anything predictable.
You've hit the nail on the head. The contextual signal theory explicitly forbids the existence of static solitons.
Oh, really?
Think about it. If a particle were to actually freeze into a perfect, unchanging soliton, its physical state would match its expected state perfectly.
And the surprisal term in our equation would instantly vanish to zero.
Exactly. And the moment it hits zero, that Gödelian driver, the LCOM term, would slap it with a massive energy penalty. It would destabilize the particle just to force it to do new computational work.
The universe literally refuses to let anything sit perfectly still.
It's the death of the frozen particle.
Wow.
Therefore, in this new ontology, matter cannot be static hardware. It must exist in states known in nonlinear dynamics as oscillons or breathers.
Breathers, like they are literally inhaling and exhaling.
Exactly. They are localized structures, yes. They hold a region of space, but they are temporally periodic. They are continuously flowing back and forth between potential and kinetic modes. They are vibrant oscillating processes rather than solid things.
So solid objects are basically an illusion. Matter is just a vibration desperately trying to avoid getting penalized by the universe for standing still.
That's a great way to put it.
Like that wooden table you're sitting at, or the metal microphone I'm speaking into right now, they aren't dead, static hardware. They are dynamic, breathing processes constantly dodging the cosmic tax on boredom.
It is a total ontological shift from a universe composed of isolated things to a universe composed entirely of connected processes.
I love the conceptual framing, I really do, but I have to play devil's advocate here.
Please do.
It's a beautiful mathematical theory. But is there an anomaly in our current observable science that this actually explains? Does this solve a real-world problem that traditional physics is currently scratching its head over?
It absolutely does. The source material spends significant time on a very specific real-world example from particle physics to prove its point. The anomaly of Kahn decay.
Okay, let's spend some time here. What exactly is a Kahn, and why is its decay an anomaly that traditional physics struggles with?
A Kahn is a type of subatomic particle called a meson. We study them in massive particle accelerators.
Like CERN.
Exactly. Now, in the standard model of particle physics, which is a current reigning champion of how the microscopic world works, decay rates are treated as static thermodynamic probabilities.
Okay.
The standard model will predict that a certain rare decay pathway for a charon should occur at a very specific, very low frequency. For example, based on the math, we might expect to see a specific rare decay happen 0.25 times in a given experimental data set.
So basically almost never.
Right. It's highly improbable. But in actual accelerator experiments, physicists occasionally observe it happening much more frequently, say finding 4 instances of that rare decay instead of the expected 0.25.
Which is an order of magnitude higher than the prediction. How does the standard model handle that discrepancy?
Mostly, it just treats those events as statistically highly improbable flukes.
Flukes.
The assumption is that the underlying probability assigned by the standard model is fixed and correct, and we simply observed a very rare high sigma statistical outlier. In experimental physics, anomalies like that are often treated as annoying noise or errors to be smoothed out with larger data sets.
Just sweep it under the rug.
Pretty much.
But the contextual signal framework looks at that exact same data and says, no, that's not an error at all. That is the engine of time working exactly as intended.
Precisely. Let's apply our Gödelian driver to the kaon. Remember, the LCOMP term actively penalizes highly expected states.
Yay.
If a kaon sits around decaying through its standard, highly probable pathways over and over again, the systemic surprisal drops. The event becomes far too predictable. The system begins to mathematically approach a local halting state.
And the universe's core programming says, absolutely not, we cannot halt.
Exactly. The LCOMP driver exerts its repulsive force. It actively drives the kaon into rare high surprisal configurations, specifically to maximize computational expansion.
Wow.
It physically forces the particle to take the rare decay path to inject new, unexpected information into the physical field.
That completely flips how we look at experimental science. Anomalies aren't errors in the data, they are the universe actively refusing to halt. They are the macroscopic, measurable signature of Gödelian incompleteness, literally forcing a physical system to generate new truths.
It takes an experimental headache and turns it into the primary evidence for a computational universe. And if we connect this microscopic anomaly to the bigger picture, we can scale this exact same mechanism up.
How big?
Cosmic. The exact same math that explains the subatomic decay of a kaon also explains the expansion of the entire universe.
Okay, let's go massive then. Let's talk about the cosmos and dark energy. Because if Gödelian incompleteness explains a subatomic fluke, and it's truly a unified theory, it has to explain the macro structure of the universe too. How does this Gödelian driver explain why the universe is getting bigger?
To understand cosmic scale, we need to bring back the other forces in our unified Lagrangian. We spent a lot of time on the L-comp driver, the surprisal penalty. But there is also the L-self term.
Right, the self-organizing one.
Yes, this is the autopoietic potential. The math models it as a Mexican hat potential, which is a very classic shape in physics for symmetry breaking.
A Mexican hat potential. Okay, so imagine a marble resting exactly on the top peak of a sombrero.
Perfect.
It's perfectly balanced, but incredibly unstable. The absolute slightest nudge will cause it to roll down off the peak and into the brim of the hat, settling into a stable, lower energy state.
Excellent visualization. That rolling into the brim represents the signal crystallizing into dense matter. The theory calls this stabilized matter the midline density layer.
So the L-self term is basically what makes matter stick together and form structure. It's the structural tension that gives us the illusion of solid objects and massive planetary bodies. It functions effectively as gravity in this new framework.
Correct. Now consider the vastness of the cosmos. In regions of space where matter is incredibly dense, where this crystallized meaning or nodal density is high, like in a galaxy cluster or solar system, the L-self potential is overwhelmingly strong.
Okay.
It completely dominates the local physics, holding all those stars and planets tightly together.
But what about the void? What about those massive empty stretches of deep space between the galaxy clusters where there is virtually no matter at all?
In those sparse regions, the L-self term is incredibly weak, precisely because there is no dense matter to maintain it. And when L-self is weak, the third term, our Gödelian driver, L-comp, is allowed to completely dominate the local physics.
And the equation for L-comp includes an expansion constant.
It does.
So in the deep void, without matter holding things together, that repulsive surprisal penalty just runs completely wild. It acts exactly like what classical physics calls dark energy.
Exactly. Traditional cosmology treats dark energy as this mysterious invisible fluid or an unexplained intrinsic property of empty space that just pushes galaxies apart.
They don't really know what it is.
But this theory explicitly defines the effective cosmological constant as being inversely proportional to the density of crystallized meaning. Where matter is dense, expansion is slow or non-existent. But where matter is sparse, in the deep void, the repulsive force of L-comp drives rapid, accelerating physical expansion.
And the actual reason it's expanding is the most beautiful part of this entire deep dive.
Oh, absolutely.
The universe isn't just inflating for no reason. It is physically expanding its configuration space because it literally needs more hard drive space to continue computing its unresolved truths.
Yes.
The Gödelian driver is forcing it to generate new spatial configurations just to hold the infinite, mathematically required shadow of its own incompleteness.
It is a stunning unification. I mean, it unites the microscopic unidirectional arrow of time with the macroscopic accelerating expansion of the cosmos under a single, rigorous logical principle. The universe expands for the exact same reason a clock ticks.
We have covered an immense amount of ground today. We've thrown out the depressing inevitability of thermodynamic heat death and replaced it with a vibrant, active universe desperately trying to understand itself.
A much better paradigm.
We've taken an abstract logical theorem from Gödel and translated it into the tangible engine of linear time. We've explored how a mathematical surprisal penalty forces solid particles to constantly vibrate and breathe, and how that exact same penalty drives the deep voids of space to accelerate outward.
We have mapped a completely new ontology. Time, matter, gravity, and cosmic expansion are no longer separate, disjointed phenomena. They are all emergent, necessary properties of a single underlying drive, the continuous resolution of informational debt.
So as we wrap up this deep dive, I really want to bring this massive cosmic framework right back down to you, the listener.
That's important.
Because in this ontology, you are not just a passive observer sitting on a cooling rock in a decaying universe waiting for the lights to go out. The sources actually refer to human consciousness as the midline stabilizer.
Yes. The midline stabilizer.
You, your awareness, and the very vibrating matter you are made of are active, necessary participants in the universe's infinite attempt to cure its own Gödelian incompleteness.
You are literally the universe computing itself.
Every single time you learn something new, every time you resolve a complex problem at work and instantly uncover a new mystery-generating form and casting a shadow, you are not just existing in time. Your mental process is structurally identical to the physical expansion of the cosmos. You are embodying the literal physical arrow of time.
However, this framework does leave us with a profound paradox.
Ooh, a paradox.
And it's a question derived directly from the math of the L-comp driver that I think is really worth considering.
Let's hear it.
Well, if the arrow of time is driven strictly by the gap between what is currently known and what is objectively true, that's appraisal penalty. What happens if a highly advanced localized system actually manages to close the gap?
Wait, is that even possible?
Imagine a future post-human society or an incredibly advanced localized artificial intelligence that manages to construct a perfectly complete, flawlessly predictive model of its local environment.
Oh, wow. If it perfectly maps its own reality, then local surprisal hits absolute zero.
Exactly. And if surprisal hits zero, the Gödelian driver vanishes. So the question is, does time for that specifically localized omniscient system physically stop?
If you figure it all out, if you achieve total perfect understanding of your environment, does the clock just freeze?
The math suggests it might.
It's a paradox that really makes you wonder if total enlightenment is actually the physical end of time itself. Think about that the next time you manage to clear out your to-do list. Until next time, keep diving deep.
Elevate your soul and discover the rhythm of life at music.condented.com. Embark on an extraordinary journey into the cosmos and delve deeper into the enigmatic characters of the lone cosmic entity at cosm.condented.com. Discover every captivating episode and exclusive extras on our podcast page, mindscape.condented.com. Tune in now and never miss a moment.